Let's start the show, shall we? So I sent out an email a little while ago. Your next homework is ready to go with the twist. So both homework 4 and 5 are available. You only have to do one. Homework 4 was done via SAS, and so SAS Glimix gives you the right answers. Homework 5 was done via Stata Emmy Logit. So pick one and do only one. The answers are close, but not close enough, as I discovered. So that's why I have 2 versions, and I plan to do the same thing for the last homework as well. So you only have to do one. That's due next Friday. It's a little shorter than last time, but it's similar in structure. So you'll get a chance to do practice some of the same concepts. So let me know if you run into any questions or problems with that. Otherwise, I think we're going to have one more day on generalized. Next week is going to be 2 special topics, generalized crossed models in the context of item response theory and associated models, and then a quick primer on longitudinal stuff. Because longitudinal is multi-level, it's a different structure of time within person as opposed to person within group. However, the reason that that is a whole separate class the way I teach it is because the addition of time requires a whole lot more consideration as a special type of level 1 variable. So I wanted to give you a few pieces of that so that we could talk about time as level 1 within the context of 3-level models coming up probably after Thanksgiving. So that's where we're headed. So I wanted to start with estimation finally, do a little bit of this. Slide 39 in lecture 5 is where I am. I want to cover just enough so that when you're looking at software and you're wondering what it does, you'll have the right keywords to search for in the software's manual, as well as to understand what not to pick in some of these things. So slide 39, lecture 5 is where we're picking up, estimation. So you will discover in running multi-level models on non-normal outcomes that the models often take a lot longer to run. So I wanted to give you some heads up to that and explain a little bit about why that is. So previously, we went over estimation in the context of normal outcomes, so normal level 1 residuals as well as normal random effects. And in that case, the V matrix that you put that puts level 2 and level 1 back together again. So remember, G is level 2, R is level 1, and you have normal residuals at level 1 plus normal residuals at level 2. The total of those is still multivariate normal, which means that you can use the multivariate normal distribution, and the answers pop out real quick. So normal plus normal equals easy estimation. For anything else, it's not so easy. So for instance, in the current context, we're talking about binary outcomes, right? Binary outcomes use a logit link or a probit link to predict them. That way, the predicted outcome can be unbounded, but it translates back into probability that is bounded. And after factoring in the fixed and random effects, the original variable is supposed to have a Bernoulli distribution. So if you have level 2 random effects that are supposed to be multivariate normal, but at level 1 it's multivariate Bernoulli, then what do you get when you put those 2 together? The answer is not a thing. I've had previous classes try to name it before. They came up with Bernormal or Normuli, which is the one I like the best, Normuli. But sadly, if you look up Bernormal or Normuli in Wikipedia, you will not find an entry for those because that's not a thing. So estimation gets a lot more challenging when you don't have one distribution to work with that holds across levels. So we need to know what the random effects are in order to figure out what the predicted outcomes are. But random effects are unobserved. So we have to do something to try and make reasonable guesses for them as the process of estimation. So there's 3 general ways that generalized multi-level models get estimated. So this holds also for the world of IRT. Anytime that you have latent variables or random effects that are supposed to be normally distributed paired with categorical outcomes. So that's this in this class. IRT models is another class. You can do things as quasi-likelihood, via numeric integration, or via Bayes. So there are older methods that fall under the name of quasi-likelihood or pseudo-likelihood. Now, when you hear those words, do they inspire confidence? If something is quasi or pseudo, like that sounds like a knockoff brand, right? Like a generic brand, how they try to have like the same names. Like if you go to Hy-Vee, for instance, you remember Hamburger Helper? You guys ever eat this? It's like a pasta mix that you can dump with hamburger, and the name brand is called Hamburger Helper, but the off brand is called Hamburger Partner at Hy-Vee, which is hilarious. Or like the Hy-Vee brand generic soda, like they have Dr. Rocket, which is Dr. Pepper, or like Mountain Rush, which is like Mountain Dew. Like they have all these things. Like think of quasi-likelihood or pseudo-likelihood as like Mountain Rush. Like it's trying, but it's not the real deal. So these are the older methods that came first, where they try to approximate the solution using some kind of linear approximation, perhaps using just the fixed part or perhaps using the random part. The reason that I point these out is that if you do nothing, they are the default in SAS Glimix. They are currently, to the best of my knowledge, still the only option in SPSS. So yet another reason I don't teach things in SPSS, because it's not possible to do these models except for in those options. One thing that I want you to know is that research has shown that the variances that you get out of these are negatively biased, and because they're pseudo-likelihoods, you cannot use them to do log likelihood comparisons. So there's no direct way to test for random effects under these methods, and so that's why I don't use them. So we're not going to do those. We're going to move on to something else, what's known as marginal maximum likelihood. So this idea has a lot of different words that are used to describe it. Numeric integration or numerical integration, adaptive Gaussian quadrature. Do you know what Gaussian means? Normal. Because Gauss is like a person who made up normal, so Gaussian means normal. So this is true maximum likelihood. It can take a really long time. You can give the model start values to try and make it go faster with respect to the random effects. When you're in this, there's no such thing as an R matrix, so that leaves fewer options if you have longitudinal data. It's not relevant for us right now. But I wanted to show you a little bit about how this works. So step one, the program has to pick starting values for all the fixed effects. So fixed slopes, fixed intercepts, all that stuff. It then has to compute the likelihood or the height of each observation given those current parameter values and the chosen distribution of residuals. So we don't know what the random effects should be for each group, but we do know that they're supposed to be multivariate normal. So even though we don't know the U's, we know their distribution. So what they're trying to do is remove the U's from the likelihood. And the way that this happens is by integrating them out. It's like area under the curve is the idea. This integration is accomplished by something called quadrature, which is where we divvy up the curve into rectangles to try and approximate it. It decides whether or not you have the right answers as to whether the sum of the log likelihoods across groups changes much, where the change much is a program-specific default. And if it's not converged, you choose new values. So it goes something like this. So quadrature means rectangles. The program picks how many rectangles it wants to use to divvy up a normal distribution. So the U's are supposed to be normally distributed. It would look something like this. So for instance, Stata's default is 7. M plus's default is 15. SAS has a thing where it just picks how many it thinks you need. In specifying these models, I have set the number of quadrature points so that the result is as close to the same across programs as I possibly can. What ends up happening in practice is that after it goes through with one set of rectangles, it goes back to the section that looked like it was going to be the best fit, and it re-rectangles just that section. That's what's known as adaptive quadrature, so it's supposed to give a better result. And the analogy that I use to explain this process is if you're going to the store and you're trying to try on jeans. So you'll notice that I have my favorite pair of work pants here. These are jean pants. They're not jeans. Like they're shaped like work pants, but they're a denim, right? I hate jeans. Is anyone else with me? Hate jeans? I notice there's not a lot of you wearing jeans. It's like leggings and stuff, like, because they're uncomfortable, right? They're uncomfortable. And it's also impossible to figure out ahead of time what size and what style would fit you, right? So depending on what store you go into, like you could be anywhere from like if you're me, like a 6 to a 14, depending on the size. And then it's like it fits differently with terms like boot cut and, skinny leg, which is not part of my vocabulary, and, relaxed fit and all these other things. Like, so if you think about all the combinations of sizes crossed with fit, and of course, let's see, there's 2 guys in here. My guess is that when you go to buy pants, you walk up to the desk, you look at the coordinate system of length and width, you take the one that matches, and you go and you pay for it, right? And that's the end of your process. Is that about it?
Perfect.
Yeah, you probably don't even have to try them on. But no, like as women, we get something like, you're a 10. What's a 10? It doesn't correspond to length or width, but it's some sort of magic combination of both. I once got really, really excited because I saw jeans that had length and width on them. And I was like, oh my God, they're going to fit. No, the solution was, as Jonathan called it, overdetermined. They were perfectly correlated. So apparently I learned that in order to have an ass this big, I needed to be 7 feet tall by its calculus, because that was the length that it came in to make the right width. So it just didn't work. Anyway, I hate jeans, but trying on jeans is an exercise in hell for most women. Like swimsuits is worse, but only marginally. But jeans, yeah. So think about me in the dressing room swearing, trying to figure out what things are going to fit, and I have to try on all possible combinations of sizes and styles to make this thing work, because I get arbitrary numbers that don't actually mean anything. So keep that in the back of your head as to why this process takes so long, because what numeric integration requires is for the model to try on U's in the same way that I have to try on pants. So let's take an example, very, very simple to keep the math easy to follow. Let's say that we have a random intercept model. I have a fixed intercept, and I have a slope for a level 1 predictor. So let's say it's been group mean centered, so I don't have to worry about anything. Let's say that my starting values for my fixed effect is a fixed intercept of 0.5 and a value of 1.5 for the fixed slope. Let's see how this would look like for 2 people from the same group. Here's my model predicting the logit that the person in this group has an outcome of 1 is a function of a fixed intercept, the fixed slope times the predictor, and a random intercept, okay? That's my model. So I have current values to plug in for my fixed effects, but I don't have anything for U. I don't know what U is going to be for this particular group. So I'm going to try on all the possible values that I need in the same way that Lisa has to try on all the sizes to figure out what works. So if I have somebody who has an X of 0 in this group, I can figure out their predicted outcome by plugging in a guess for U. So if I have a normal distribution for U, I can say mean 0, variance 1. I'll try on, say, a U, not theta, wrong class, oops, of negative 2. If I plug in a negative 2 for my U here, I end up with, let's see here, minus, the logit here, the total logit ends up being minus 1. If X is 0. Because I have, let me get this straight. Yeah, there we go. So if I have somebody who got a 1, then the probability of a 1 from this logit is 0.27. The probability of a 0 is this. If I do the same thing for the next person, their probability of a 1 is much less. If I multiply these 2 numbers together, if I know they both got 1s, I get that. If the first person got a 1 and the second person got a 0, I'd multiply those 2 numbers together and get something else. Now, if I go through and try to figure out how likely is it that a group has a U of negative 2 in a normal distribution? Not very likely. So we downweight that result as a function of the width of the probability of observing a theta of -2. So we end up multiplying this together and you get this. Next set, let's try on a theta of 0. Here's the predicted logits. Here's the predicted probabilities that they translate into. Multiply those together, get that. Okay, how likely is it that you have a theta of 0 or u of 0? It is pretty likely because u is right in the middle, so we upweight it and we get that. So basically what it does is calculate the predicted logit of the score that you got trying on these different possible values of u, where the number of possible values that they try on is the number of quadrature points, is the number of rectangles. So for every single iteration, if you had, say, 15 quadrature points like they do in M+ as a default, every single group would have to try on 15 U's for every single person to come up with the likelihood for that group. So by trying to figure out what the likelihood is for each possible U and then summing those up across by weighting the U's by how likely they are and then summing, you end up by integrating it out. That process of trying on takes a really long time. The other problem is what happens if you have more than one U. So if you picture like trying on 15 sizes of jeans in one style, what if I want to try on 2 different styles and cover every possible combination? Right? This. So if I have one U that has 15 quadrature points and another U that has 15 quadrature points, how many tries does that take? 225. So every U you add exponentially increases the number, the computational complexity. And that's why it takes a long time. So the good news is that after this process is over, the log likelihood value that you finally end up with is a true likelihood in the sense that you can use it to do deviance comparisons, likelihood ratio tests, and all that good stuff. But getting there can be tricky. And so for situations in which there's a lot of random effects or a lot of latent variables, sometimes ML just craps out. It can't handle it. And that's when people turn to things like Bayesian estimation, in which they try to draw from a distribution of U's rather than try on all possible values. So that's where those sorts of techniques have really come into play more recently as ways to get answers when ML just can't give them to you. So this is to say when you're working on your next homework, a lot of you have gotten used to rerunning all the models every time you add something, you just hit run all. Don't do that. It'll take a while. Just run the one that you need, because otherwise you're going to wait at your computer much longer than you may need to. So there. A little bit about estimation. You can highlight it and hit run in either program. In SAS, the keyboard shortcut is F3, and in Stata, it's Control-D in Windows. So, yeah, you can just run that one little chunk. Yep. Okay. So your homework is using logits and adding some random effects, so you'll get a chance to play with this. The other example that I had previously built is for count outcomes. So I wanted to give you a little bit about that. So we've talked about categorical. Count is another type of what's known as a discrete outcome. Outcomes that can only take integer values versus things that are continuous, where the response is truly in between integers, continuous in that sense. So counts are tricky because oftentimes they have extra considerations that the model has to address simultaneously. Rather than think about it as discrete versus continuous, this is the way that I like to think about those. There's models for distributions that look skewed, and those include counts that are discrete as well as things that are not discrete that are continuous, like response times. And then there's other models that deal with counts that have a buildup of 0. or continuous data that has a buildup of 0. And that's what's known as zero inflated, and what I tend to refer to as if and how much. And so I want to walk you through some of the options for that as well. So counts. What's the smallest number that a count can be? 0, right? You can't have negative, days in the hospital, or negative numbers of cigarettes, or numbers of times that I said shit today. All my favorite count variables. So the link that we use to predict count outcomes is the natural log. The natural log then takes any number that is above 0, and it stretches out the ones on the small side and it reels in the ones on the big side. So a log transformation is commonly used to make skewed data to the right look more normal. It also sort of spreads out the left-hand side, but it keeps the predicted counts positive. So to unlog it is when you exponentiate. So it's written like this: the log of the predicted count, and then the inverse link for it is to unlog it, is to exponentiate that parameter. So for instance, if the model predicts a log count of 1.098, that translates into e to the 1.098 is actually 3. Likewise, if you have a log of the predicted count that is -5 and you exponentiate that, you end up with this very small number. So the predicted count always stays above 0, but it takes non-integer values. So that's why you have to make a distinction as to what the count is versus the predicted count. You can have intermediate values be predicted in the same way that you can have intermediate values predicted for probability between 0 and 1. So all of these models that predict skewed things, counts as well as for continuous data, use a log link. The question is what kind of variance goes with it, and that's where the distinctions come in. So the basic model, sort of the off-the-shelf, is uses what's known as a Poisson distribution. Have you seen this before? It means fish in French, apparently, I learned. Not that that's relevant, but just fun fact. I stole this picture from Wikipedia, as I'm prone to do. The Poisson distribution has a unique feature in that its mean and its variance are also tied together. So in binary data, the mean is a function of the variance. It's the mean of the probability of a 1 times the probability of a 0. In cat data, the Poisson says the mean and the variance are the same number, and it's given by this parameter that's known as lambda. So if you have, say, a mean of 10, that's the blue dots here, this is what a distribution would look like if its mean were 10 and its variance were 10. That looks like what? How would you describe this blue shape? Kind of normal, right? It's nice and symmetric. And it turns out once you get past like 7 or so, then count distributions tend to look like normal distributions. The only catch is that count distributions are discrete, and that's why they have these bubbles here, because they don't allow for intermediate values. They're integers only. Whereas if you look at something like the purple one, this is a count with a mean and a variance of 4. And because the counts can't go past 0, it starts to get asymmetric. And a count of 1 might look like this. So it builds in the idea that your distribution has to be skewed if the mean is very small. But it is frequently the case that there is more variance than the Poisson would predict. The variance exceeds the mean. So if it's less variance than what's predicted, it's called under-dispersion, which is pretty rare in practice. What's far more common is over-dispersion. So we may have to change to a different distribution to allow there to be more variance than what the mean predicts. There's also a different distribution you have to change to if there are no 0 values. So if 0 isn't possible, for instance, if you have archival data from a hospital, and what you're interested in predicting is, say, infection rate from like number of days in the hospital, or you're trying to predict how long people have to stay there. The minimum number of days that someone is in the hospital has to be 1 if they're in the data set. Otherwise, they wouldn't be there. So if the minimum count is 1, then you need something called a zero truncated distribution, and it is not the same as if you just subtract one from each of the scores. I tried that once and it didn't work. Another problem is if you have too many zeros. And so there's a couple different ways to fix that in that case. So here's the first one. Here's some really ugly formulas. This thing is called the negative binomial. It shows up in the context of how long do you have to go before you hit enough trials in the context of the binomial, but it's used as a backdoor to get skewed looking distributions that are related to Poisson. So rather than focus on the scary looking formula, I'll show you what it looks like. So negative binomials take Poisson distributions and stretch them. And there's a parameter for sort of stretchiness that is, it's called dispersion. And it's parameterized differently across software packages, but the basic idea is that it boils down to this, where there is a multiplicative function of the mean that gets estimated as to how much extra variance there should be, and the variance changes as a function of the mean. So I made some pictures in Excel rather than stealing them from Wikipedia this time of distributions that differ in their variance but are the same with respect to their mean. So if we look at red and blue, red is a distribution that starts with Poisson but adds this k stretchy factor so that the variance is higher than the mean, whereas the Poisson one that's in blue, the variance is the same in the mean. So blue is more concentrated, red sort of spreads out and has a little bit more expected skewness. The same is true for purple versus green, where green is the Poisson where the mean and the variance is 10. The negative binomial version still has a mean of 10, but it has more skewness to it. So this ends up working pretty well for count data that have more skewness than would be expected, which is like almost all of them. So we're going to do an example that uses that. The nice part about this is that whether or not you need the negative binomial is a testable hypothesis. So whether or not this stretchy thing is either equal to 0 or 1, depending on how it's parameterized in your software, you can test whether you need that extra stretchy or whether Poisson is sufficient. So we will do that one. So here's 0 truncated, and then I have stuff about other outcomes, but I wanted to show you what this is going to look like. So I have an example that I built. Example 5b, let me make sure I'm streaming here since, some of the folks aren't here today. I borrowed some data from the Rabahethskis and Strondal book that actually showed up in this Stata help guide. So this is from their example 2 in the Men-Breg routine, which is their version of negative binomial for mixed effects models. So the outcome is the number of deaths among males due to malignant melanoma, so skin cancer. These are multiple counties nested in regions, which in turn are nested in nations. So they modeled it as a 3-level example. However, there were only 9 nations in the data set, and one of them, Luxembourg, only had 3 regions. So I ended up using a subset of these data that kicked out Luxembourg, and I'm going to treat it as 2-level and then show you what it looks like if we control for nation within 2 levels rather than doing it as the 3-level. So because we have a count outcome, we're going to work with Poisson and negative binomial, try to figure out initially which one would be better, and then see if UV exposure predicts it. So I have 351 counties that are nested within 77 regions. So here's the data manipulation. I computed region means for the count of deaths and for UV exposure. I then created within region versions of those variables so that I could make some pictures and do some descriptive stuff. So in terms of the N per region, the regions have between 1 and 13 counties contributing to each, so there's a bit of variability there. the mean number of deaths per region ranges from 1 to 160, so quite a bit of variability there. And it looks like UV exposure was already centered at 0. I honestly have no idea what the scale of this is because it wasn't included in the description, but it ranges from -7 to 12 at the region level. So here are graphs of the region level variables. Deaths is on the left side, and UV exposure as the predictor is on the right. So even at the region level, we see quite a bit of skewness in the level 2 information. Here are level 1 descriptives. These are the number of regions within each of these nations, as well as death count, the within region part of death count, so using group mean centering, and the same thing for UV. And I did that so I could make some pictures. So the top two here. Deaths on the left, within region deaths on the right. So the picture on the right is deaths minus the region's mean. So this is like the group mean centered version of the variable. Now this is an outcome, so I'm not going to do this in the model, but I did it to make a point. The one on the left is clearly a count outcome. It looks like there's some zero inflation, meaning there's like more zeros than would be expected based on this distribution, as well as a fairly long tail indicating some skewness here, over dispersion. However, part of what we're seeing here is the dependency of counties nested in regions. Because when you take that dependency away, by doing this sort of by brute force just for demonstrative purposes, by subtracting the region mean, this is the distribution that we end up with. It looks a lot more normal. So when you're making pictures of distributions, it's not enough just to look at sort of the level 1 outcome with all the information in it. Trying to figure out what is going to be left at level 1 after factoring out the dependency is going to be more useful. But in this case, we still have sort of the same, a little bit of over dispersion here, but it's not nearly as egregious as what it was in the left picture. So the dependency is part of the reason we see some of this extra skewness as well as this zero inflation. And the same thing is true for UV exposure at level 1. When you look at just the level 1 part of it, it looks a lot more normal. All right, so here's all the same stuff in Stata, all these techniques you've seen before. So first thing I wanted to do is look at what kind of variable UV exposure was. So here's a fun fact. In the Stata manual, do you know what they do for UV exposure? They just put it in the model, and then they talk about it. And I was like, is that a level 1 variable or a level 2 variable? And I went and looked at the data set, and it changed across rows. So what does that mean? If a variable changes across rows when you look at the data set, is that a level 1 variable or a level 2? Level 1. But they just went and stuck it in the model. Cool or not cool? Not cool. You think I'm making this up? Stata 16 Min Brig Manual. These people should know better. I'll let that pull up. So yeah, they just went and stuck it in. And I could tell just from looking at the data set that it had to be a level 1 variable. So what would be one of the first things you might want to know about a level 1 predictor? How do I know if I need to worry about smushing or not? The ICC, right? So yeah, this is where remarks and examples. So they're like blah, 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 hangman, blah, 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 gamma function, hard stuff, more hard stuff. Here's some code. So here's example 1. And here is example 2. Number of deaths due to malignant melanoma. And there they go. And UV. Done. Stick it in the model. It's already mean-centered, so that 0 means something. But yeah. And then they talk about it. Now, so I did an intraclass correlation. And you know what it was? 0.98. So is this a level 1 variable? How much of it is a level 1 variable? Like a percent, right? 1.6%-ish. The intraclass correlation is 0.98. 0.98 is the proportion of total variance in UV that is between regions, which means that within is like 1%. So if there's going to be an effect of UV, it's probably going to be a level 2 effect. Some regions have more UV exposure. It varies very little across counties, in the same region, which stands to reason, right? Because they're all like the same part of the earth. But I'm going to put it in at both levels, make sure that we don't smush it, but just know that the effect that it's carrying is probably a level 2 effect. But the first question, though, in predicting number of deaths as the count outcome is what kind of model we need. So I'm going to show you 4 possibilities to try and figure out what the extent of dependency is in number of deaths of counties from the same region, as well as the extent to which there's still that over-dispersion, there's still that extra variance after we account for the dependency. So I have a single level model over here on the left where I have just a fixed intercept and no random intercept, and I have one on the right where I've added a random intercept. And I'm going to estimate single level and 2 level versions of both a Poisson and a negative binomial so that we can compare their fit and figure out if both over-dispersion and dependency appear to be a problem in these data. So a few things are different in the code. We're still in proc glimics, but now we've switched out what the underlying model is. So for count data, I'm using a log link, that's the natural log, and a Poisson distribution to start with. To do so in Stata, it is called ME Poisson, where ME stands for mixed effects. To unlog the count, iLink is going to do the exponentiation for us. Here's what it would be in Stata, writing it out by hand. So here's what ends up happening. The log of the count of the average number of deaths is 3.3. If I exponentiate that, so e to the 3.3, that's 28. As it should be, because when I ran descriptives, 28 was the mean number of deaths. So I know the model is working, because that's what it should give me. Here's the same model, but switching from Poisson to negative binomial, seeing whether or not the variability that's implied by the model is different than the variability that it should be. So let's do some foreshadowing. The standard deviation of this variable is 38. So do you think that a Poisson is going to hold? Remember what Poisson says about the variance? Same as the mean. Do you think 38 squared is equal to 28? Because I don't. So if I swap out Poisson for negbin, and I swap out ME Poisson for min-breg, I end up with some new information. So you haven't seen this yet. this thing right here starts to show up for different distributions. Pearson chi-square over degree of freedom. All I know about that is that it's supposed to be 1 if the distribution fits your data. 1 is not 51. I'm also pretty sure of that. So this 51 is indexing that a variance of 28 is probably not going to work for these data. Here is what happens after we switch to the negative binomial. It goes down to 1.65. That's much better. You end up with this new parameter right here, which is a scale factor. It is 1 under Sass's parameterization if you have a Poisson model. So this is a multiplicative factor that enhances the variance as a function of the mean. So the model predicts much greater variance now as a result of this. And you can see this if you look at the standard error. So the standard error around the mean from the Poisson was predicted to be 0.28, whereas now it's 1.5. So the model is building in a lot more variability as what it's predicted to have for this variable. By the way, Stata gives you this in a different form. It gives you the natural log of it. So it's the same number but just on a different scale. Something else that we haven't talked about yet, but that you will see on here in SAS output, I couldn't figure out how to get it out of Stata, are gradients. So I've added this keyword gradient to my options. You also now know what this means. So method equals quad. You know what quad stands for? Quadrature. Q points equals 15 means I would like 15 rectangles, please. Why am I doing that? Because I'm trying to establish comparability across programs. Stata defaults to 7, M+ defaults to 15. SAS has no default from what I understand. But in your homework, I'm asking you to change this to 7. That way it won't run so long. Gradient is a troubleshooting option that describes how well each of your parameters has been estimated. More technically, what it is the first derivative of the log likelihood function with respect to that parameter. So if your parameter is really the best version of itself, it's at the top of its function, it's the most likely, the slope at the top of the function should be 0. Otherwise, it's not really at the top of the function and the model converged prematurely. So these numbers that are super tiny in scientific notation are good. This indicates that these are relatively trustworthy because their gradients are very much near 0. So we can do a log likelihood test to see whether or not we need the dispersion parameter, but it looks pretty clear that we do. Before we call it good, though, we need to make sure that we also account for the dependency of regions. So here is a model switching back to Poisson, but adding a random intercept. So ME Poisson and log Poisson. Here is my Pearson chi-square over degrees of freedom. It's 13. So the original Poisson single level was 51. By adding a random intercept, it went down to 13, so that's better, but still not very good. Note the gradient here on the random intercept has actual values in it. It's closer to not being 0. So you want to watch for these things as you're adding random effects in particular. If it's really unstable, these numbers will get crazy, and even if the model looks like it's converged, you probably shouldn't trust it. We now have a predicted log count conditional on a region that has a random intercept of 0 of 3. If I unlog it, that's a mean of 20. So the mean has shifted because it's unit specific. It's conditional on the random intercept equals 0. I did my Cove test right here to test whether or not I need a random intercept. The 0 just means take the only thing that's in the G matrix, the random intercept variance, and pretend it's not there and tell me what the log likelihood would have been without it, which is that number right here, and there's the difference. So 13,249 is what the model without the random intercept should have gotten, and it is that. So it did get it right. In your homework, I checked, and it did get it right as well. So you should be able to use the Cove test option. I'm also going to ask you to do mixture chi-squares in your homework. They are provided sometimes by SAS. Do you remember how to do that? We talked about that before. It's 0.5 times the p-value for the lower degrees of freedom plus 0.5 times the p-value for the upper. So for this instance right here, when we add a random variance, that's 1 degree of freedom's different for a random intercept. So it would be 0.5 times the p-value given 1 degree of freedom plus 0.5 times the p-value giving 0 degrees of freedom. The latter works out to be 0, so you're allowed to take your p-value and cut it in half, and that will be the mixture one. So SAS is doing you a solid by giving it for you, in this case. Stata does the same thing when you're just testing a random intercept. Last but not least, a model that has both overdispersion, so negative binomial, and the random intercept. We can see if both of those things are necessary. So I'm adding a random intercept for regions in Menbreg, as well as a random intercept here. I'm doing 2 different tests within SAS. So now the G matrix is going to have a random intercept in it, and it's also going to have an overdispersion parameter. So 0 dot means take out the random intercept, but leave in the overdispersion. Dot means leave it alone. It's going to be the second entry in the table. And to test the overdispersion, it's the opposite, except the null hypothesis is 1, given the way that SAS parameterizes it. This is something you'll have to look up inside your program manuals to figure it out. And when we get all the way done, our Pearson chi-square is down to 1. Hooray. I suspect these data are simulated, because that rarely happens in practice. It looks like I have a considerable amount of random intercept variance, as well as a scale factor. And here are the results of my likelihood ratio tests. So we need both of them in order to keep our model working. So we have overdispersion even after the random intercept. So we'll keep both, and then we can add it together. Here's a confidence interval for the random intercept in log counts, and if you exponentiate, you can get into counts. So 95% of the regions are expected to have a death count on average, somewhere between 3 and 128. And we can look back to our original descriptive statistics to see how well that jives. So it looks like the model is undershooting the maximum a little bit, but there's not a lot of people out here. So the 95 confidence interval stops about right here. So max is 160 in the data. The end of the confidence interval is 130-ish. So this is all due diligence in trying to figure out what the right kind of model is. Now we can add predictors. So, questions so far?
So can I go back to page 7 of the overdispersion? You say the dot means to test the overdispersion and the 1 to test the Poisson distribution?
In this case, what the dot means is leave the random intercept in, because that's the first term. So these are listed in order of the terms in the covariance parameters table. And the 1 is saying make the scale parameter to be 1. That's what it is if it were Poisson. How I knew that is that I had to get into the SAS documentation and look at exactly how it's parameterized. Sometimes it's 0, sometimes it's phrased as 1, sometimes it's given as the law as a 1 over the scale parameter. So different software does it a little bit differently, but once I found it in there, 1 is what it is if it were Poisson. I couldn't figure out how to get it tested correctly in Stata. But in theory, if you just look at the difference in the -2 log likelihood between the model that has the negative binomial and the model that has the Poisson, that's a likelihood ratio test as a nested model. Because there is no overdispersion in the Poisson, and there's extra overdispersion. So it's like if you take it away, it simplifies to Poisson. Yeah, these generalized models are really about the job security. Like, it's hard enough to figure out how the model works, but then you have to figure out how it works in each of your packages. So, that's why I have a job. You can learn this stuff too, and then they'll change it in the next version, and you'll have to figure it out again. That's what will happen. So, but yes, once you do figure it out and it works, though, there's like no feeling like it. It's like, I win! I beat the SAS! So, anywho, so we have a 2-level negative binomial model. The U's at level 2 are still supposed to be multivariate normal. However, after you factor in the fixed effects and the random effects, the E's at level 1 follow a negative binomial distribution. That's the idea. So let's put some stuff in our model. How about region mean UV? So this is the level 2 part of the UV predictor. So 98% of the UV predictor was level 2 variant, so this is really where the action is going to be. Once again, requesting predicted outcomes for a 1-unit change in this predictor to demonstrate the difference between model scale and data scale. So we have this as our new set of fixed effects. So the intercept, what's my scale here? The intercept of 3 is what? Outcome is death count. Something nice and cheery for a Thursday. 3 means what? 3 dead people? No, it's not that simple. It's a mean. Just like any other intercept, it's conditional. It's specific to a group that has region mean UV exposure of 0. But what is this metric? It is unit specific, but what is the scale? 3 of what? Yeah, you'd think it'd be people, but it's not. Log people. The log of the count is 3. And I don't know about you, but I can't do exponentiation in my head. Good thing I don't have to. E to the 3 is right here. So my middle estimate statement asks for the intercept conditional on region mean UV equals 0. That's the coefficient in logs. If I unlog it, inverse log, that works out to be a mean of 20. So that is specific to a region that has UV exposure equals 0. It is also specific to a region that has a random intercept for death count equal to 0. In that region, 20 people are predicted to die from skin cancer. Now, do you think that UV exposure is bad for you? It's supposed to be, right? That's what I thought. Turns out, unless UV is backwards, if I have a variable called UV, I think higher values lead to more UV, right? That's what I would think. So either I'm wrong or the science is wrong, because that coefficient is negative. So I have no idea what this variable means. But what it does say is that as UV goes up, deaths go down. So this is level 2, right? Region mean. So for every unit more UV your region has on average than other regions, more question, your region's death count in logs goes down by 0.08. So I asked for predicted log death counts. So here's what it would be. Goes up by 0.08 for -1. Then it goes down by 0.08, down by 0.08. So the difference in log count for regions that change in 1 unit is equidistant. It's the 0.08, 0.08, 0.08. If I translate those log counts into real counts, which is this last column over here for mean, those differences are not equidistant. The same slope effect has to slow down as you get closer to a count of 0. The same thing happened as a logit. So this is to say you cannot unlog a slope either. You can't unlogit a slope and you can't unlog it. What you can do is create predicted log counts and then unlog those to show an effect.
So here, if you say the count goes down by 0.08, but you cannot know exact number of persons like you do the intercept.
That's right.
Just minus the difference,
Yeah, the log count goes down by 0.08.
but you don't know the number of persons.
You have to so what that translates into in terms of number of persons depends on where you are on log count. So like if you're down at like log count 5, that slope has less of an effect than if you're up at log count 40. The closer you get to 0, the less actual change there is. Yep. So complicating things, all this fun stuff I learned across software. So in SAS, when I do iLink here, that's what gives me that extra column of mean and standard error of the mean. So that gives me probabilities if I'm in logits. It gives me counts if I'm in logs. And those are all still unit specific. So like I can get my calculator out and given that log count, take EXP to that and I'll get this number. So it's just doing a quick mathematical translation for me for convenience. I learned that this is not the case of what Stata does. So these two lines in Stata look like they would be doing something very similar. Margins in Stata asks for predicted outcomes across values of the predictor specified where the first number is where it starts from, the number in parentheses is by, like per unit increment, and the last number is where it ends. So like this is, give me predicted outcomes for this covariate starting at -1 in increments of 1 up to 1. So it's basically writing those 3 estimate statements for me. Predict XB means do it in the scale of the linear predictor, meaning log count, and predict it from the fixed effects. If you leave off predict XB, it gives it to you in counts, like real people, but they're not unit specific. They average, they're the marginal counts, averaging, integrating out over the random effects. So they don't match. So the counts that you get are not just the exponentiated versions of these. They are different completely. So they're marginal rather than unit specific. And for that reason, I didn't ask for any of those in your homework. So I was like, well, shit, what they mean is different. I can't say that. There's shit can't 2 for today. That actually makes that 3. So if I can show you just a second what those actually mean. Let me get out this Stata output, for example, this example. There we are. So margins for the predicted log counts So the first table here gives me 3.12, 3.03, and 2.95. That's for pred XB. That is the same thing that SAS gives me right here. So it's giving me that part. But whereas SAS gives me the corresponding real counts that go with those numbers, 22, 20, 19, what Stata gives me next are 31, 29, and 27. These are not conditioning on random intercept equals 0. They're marginalizing across it instead. So it's a very different result. I don't know why they do that, but I know that they do that. So if you're using Stata, it would probably be better just to stick with the fixed effects and do the exponentiation yourself. That way you're staying within the same metric for everything that you're talking about. Because this is a level 2 effect, it's going to account for random intercept variance. And lo and behold, 19% of all the reasons why some regions have a higher death count than others is because of their UV exposure. If we add a level 1 predictor, we can then predict why some counties within regions have higher death counts than others because of within region fluctuations in UV counts, of which there are not very many. Unsurprisingly, within region UV doesn't seem to matter much. Why do I say that is unsurprising? I'll give you a hint. It's not because I know anything about skin cancer. The ICC for this predictor, do you remember how much of the information in UV was at level 1? 1%. This is functionally a constant. I do know that constants don't predict things very well. So yeah, for that reason alone, I'm not surprised. But even that notwithstanding, these effects are in opposite directions. I found that interesting. The contextual effect, though, is significant, meaning that we can't smush them together, meaning that the example in Stata is wrong. Sorry. The within effect is positive, the between effect is negative. Here's the hard part. What do I do to give this an effect size? So for a level 2 effect, I could look at pseudo R square for the random intercept. What can I do with this? Does anybody know? Because I don't. I'm legitimately asking. What I have is not a residual variance. I have this scale thing that refers to the stretchiness of the variance, but I don't think it's meaningful to see if that changes, like percent reduction in scale, because that's not variance, it's stretchiness of the variance. And what did we have in Logit land for effect sizes? The thing that I hate. What do people do in like logistic regression to give effect sizes? The thing that I hate. 2-word phrase, OR. Odds ratios, right? I don't know of anything analogous for this. I honestly have no idea what to do for effect size for this. The only thing that I can think of is to take this t value and convert it into an R or a D. That's the only thing that I can see, because there's no variance that I can put my hands on to be explained. There's no way to exponentiate a slope. You can't do that. So, nah. I don't know. And for the same reason, you'll notice that I didn't do an ICC for death count to begin with either. Because that was the thing that I tracked down across textbooks, that someone stuck a 1 in and no one knew why, and no one knew what the right answer would be. So there's different variants of formulas for ICC that I found for counts, but they usually use some function of the mean, because the variance and the mean are related, as part of the ICC, which means the ICC would be different at different points along the variable. And that makes me squishy. So I don't know what to do with that either. It did seem to reduce the scale factor a little bit though, which means it's sort of that idea, but I don't think that works. Here's a random slope of within region UV, as well as another example of how to test random slopes using Cove test. So in this case, I have 4 values that I have to fill in. It's in order of the covariance parameters table. So you can always run it and look at that and then come back. So the covariance parameters table lists the random effects first and then the scale factor last. The random effects are always specified in the order in which you wrote them on the random line. So dot means leave it alone, means leave me the random intercept, take out the random slope and its covariance with the intercept, and then dot leave in the over-dispersion scale parameter, and do a nested model comparison. The same thing can happen in Stata using likelihood ratio test. So I save the results from the previous model as fixed, I save the current model as random, and then I asked it to do a comparison. And here is the result of that co-harm statement. It's giving me the -2 log likelihood of the previous model without the random slope and the covariance. The difference in -2 log likelihood is right here is your test statistic and the mixture chi-square that goes with it. So would you like to see how I would get a mixture chi-square so that you can do it for your homework if needed? Would you like to see that? Just, hypothetically. My friend chi-dist in Excel. So if I have the chi-square value, in this example it was 7.59. I have the degrees of freedom using the so-called conservative or naive approach, which is the number of parameters added. df minus 1 I also need. So the idea of this mixture chi-square is that in situations in which the random slope variance would be positive, the sampling distribution for adding it and its covariance would be a change of 2 things. But if the sampling distribution were allowed to go negative, then we would only be adding the covariance. The other thing would be a 0. So this is supposed to mimic the idea that sometimes, if the null hypothesis were true, the random variance would go to 0, in which case we've only added 1 parameter and not 2. So we can do the p-value for degrees of freedom equals function chi-dist, chi-square value, degrees of freedom. Okay, so that's the p-value if you just use regular old degree of freedom. The p-value for df minus 1, same idea, chi-dist, chi-square, that degree of freedom. Now the mixture p is 0.5 times the p-value for degrees of freedom 2 plus 0.5 times degrees of freedom 1. And that's what it should be, if my math is correct. Yep, my math is correct. Hooray. So that's where that number came from. I found in playing around with this that once you try to add a second random slope, it no longer gives you a mixture p-value. Don't know why. Stata's output does not give you a mixture p-value, so you'll have to find it yourself, but this is how you do it. So it's equally weighting the combination of the p-value for degrees of freedom of 2 and a p-value for degrees of freedom 1. That's how it works. All right. And we're out of time. But the rest of this is showing you what it would look like to control for nation as a fixed effect rather than as a third level. So I'm adding in main effects of nation as well as interactions of nation with UV and showing you how to get what those simple slopes would be for each of the nations using statements and all of that. And then words, because I don't just bring candy, I bring words. Ta-da! The end. So, questions?
Can we come back to the 11 of random variable slope?
Page 11. There I am. Yeah.
So the first dot, you just leave the first level fixed effect alone.
No, the dot is leave the random intercept in there. So we're testing just the new addition of the random slope and its covariance with the random intercept.
The first one is the random
Yeah.
intercept.
Yeah, leave that one in, is what the first dot is saying. All right, any others? All right, then have a good weekend. Let me know if you need any help with your homework, and I will see you all next week with new stuff. I'll let you know when that is ready for download.